Hi, my name is Eric Jamois. Thank you for joining me in this ADMET Predictor interactive tutorial dedicated to substructure and Markush searching. For reference and consistency with other tutorials, I'm using version 10.2 of ADMET Predictor, which is also known as APX.2. Our topic for today will focus on the cheminformatic functions of ADMET Predictor. So we're going to cover explicit substructure searching, but also Markush searching. And we will also see how you can analyze data sets using smarts filters. So we'll see how we can use some of the pre-built filters that have been included with the software, but also how you can make your own. So we're going to start with the substructure search aspect, and we're going to load a file of a little bit over 10,000 compounds, which is this enamine diversity set. So we're going to open this set of about just again a little bit over 10,000 compounds. And the first thing we're going to do is to look for compounds that contain a pyridine ring. And one of the ways you can do this in the software is under Edit. You have the ability to query by substructure, by structure, and also by property. The quick keyboard shortcut for this is Control-Q. And you have multiple ways by which you can enter this query. The really easy way to do it is through MetChem Designer. So you have this MetChem Designer option here, and if we want to query for a pyridine ring, we can very simply sketch a pyridine ring, okay? And then the way we transfer it back to the substructure search window is by pressing this left arrow keys that says transfer the structure back to the caller. Okay, and there's different functions here to use exact matching or substructure matching, etc. So for the purpose of this exercise, we're going to look for, again, substructures within this molecule, this set of molecules containing a pyridine ring. So we've set our search here, and all we need to do is to click OK. So that will start the search. It's actually very fast, as you've seen it, barely the blink of an eye, and it's returned the set of compounds that contain a pyridine ring. These compounds are highlighted here, so we could just go down the list and see the compounds that contain a pyridine ring. One of the easy things you can do is actually store that as a column. And if you go to one of the selected compounds and go to modify attributes, you can add an attribute that corresponds to the presence of the pyridine ring. So you can say add attribute. This is going to be a constant value. Okay. And in this case, it's going to be a text. The attribute name is going to be pyridine. And since these are the compounds containing, we're going to say yes, it contains one or multiple pyridine rings. So we've added a pyridine column here, again, with the compounds actually containing one or multiple pyridine rings, getting a yes annotation within that column. And now if we want to revert that selection, there is a very easy way to, with Control-I, that's a keyboard shortcut, Control-I allows you to invert that selection. So now we're selecting all the compounds that don't contain any pyridine ring. And the same thing, we're going to say modify attribute. So right mouse click on one of those compounds, add attributes, constant value, and this time we're going to say no and O. No. Okay. And we really don't need the selections anymore. And to deselect everything, you can enter, you can either go under Edit, Deselect All, and that maps to Control D for deselect. So Control D, we have nothing selected anymore. So one of the interesting things you can do in chart 1 is to plot the compounds that contain one or multiple pyridine rings. So this is a categorical column. Obviously, it says yes or no, but it will display in ADMET Predictor as being a yes or no. And by clicking on this column now with your left mouse button, you can see that you've got 1,783 compounds which contain a pyridine ring. And then you can just go through all of these compounds and notice that it's also displaying for you the available compound attributes for these molecules. So, okay, so we're going to shift gears a little bit now and get into something a little bit more sophisticated, which is a Markush search. Okay, so what we're going to do now is we're going to search for compounds that contain either one or multiple three-membered rings, but three-membered rings which can be of different kinds. So either a cyclopropane or an epoxide or the nitrogen equivalent, which is an aziridine. Okay, so, and we're actually going to use a shortcut way of doing this. Previously, we used the edit query by substructure. That's what we did before. There's a different way of doing this, which is a little bit faster. And that involves using the attributes function. So, and that is found under data. Okay, you can directly add compound attributes corresponding to a query. So again, under data, add compound attributes, and now you would select query. Okay. Now we're going to clear this query. We're going to our previous query, which was this pyridine ring, and similarly, we're going to go into MedChem Designer, okay, and enter our basic cyclopropane ring here, but we're going to make our selection a Markush structure by selecting this atom here, and instead of selecting set atom type, we're going to allow multiple atom types to map to this location. So we're going to allow a cyclopropane, an aziridine, that's the nitrogen, or an epoxide, that's the oxygen. Okay, and this now becomes our Markush structure that we are, in a similar way that we've done before, we're sending it back to the caller, and this is now our query element. And we will give it a name a little bit more explicit than molecule 2. And we're going to call it 3MB ring. Okay. And we're going to say OK. And our structures come back. And we can easily rank them. So now we have a new column which says 3MB ring, and we can sort based on this column. So we see that there are some molecules that contain 3, others that contain 2, and many that contain none. Now, if we want to do a similar graph as what we've obtained before, similarly, we can use chart 1, now using the 3-member ring column, and we've got either 0, again, the majority of the compounds don't contain any 3-membered rings. They can have 1, 2, or 3. And if we click on one of these, then we can see, for example, the compounds that have 3 3-membered rings, and there's only 2 of them. So again, it's just a very easy way to have access to these compounds. Okay, so let's shift gears and see how we can use and create query files, which are .cqf files. These are files that are within the software. They've been pre-built to provide search capabilities for certain features. And you can use them as is or create your own. In a standard ADMET Predictor installation, they're going to be located in C, Program Data, then Simulations Plus, and then whichever version of ADMET Predictor you have installed. So I'm using 10.2 right now, so you'd be looking at these files called with extensions.cqf. These are query files. And if you're planning on working with these files, the best option is to, especially if you're going to modify them, it's going to be a good idea to copy them first to your local directory. So I have copied a few here, like drug-like filters.cqf or reactive metabolites.cqf or toxalerts.cqf. So say if you wanted to use this drugfilter.cqf file, but before we use it, I'd like to show you a little bit about how these files are structured. So you can open them in Notepad, which I'm doing right now. And they are structured with a first query name, and that's what we may call like the head query. In this case, it's called DLF underscore score, and DLF standing for drug-like filters, okay? And so this is the head query, and under this query, we have several subqueries, okay? So, and the way that they are structured is you have the query names, or the subquery name in this case, and then you have a few comment lines which describe the query itself and what you're looking for, and then this line containing the query. So SLQ indicates to the software that you're going to be issuing a structure query, because there are other kinds of queries like property related queries. And this is the smarts expression, which contains the pattern. And then there is a letter which indicates the kind of mapping that is to be performed between the query and the structure. And there's three different kinds. There is single mapping, full mapping, and unique mapping. Okay, so S stands for simple, in which case it'll return the first occurrence or the first mapping of the query onto the structure. There is full mapping, which is so all combinations, and then there's unique mapping of, again, the query against the structure. And then the score of 1, meaning that finding the pattern will result in a score of 1 for that function. So here, if we're implementing a penalty system where we're giving a 1-point penalty, for example, to the structure for meeting that criteria, then each one of these queries can result potentially in a score of 1. Note that if the occurrence is multiple, which would actually in this case can't occur because it's a single mapping, but anyway, even if there was multiple occurrences of that pattern in the structure, it would only record a score of 1. Okay, so however, a score of 1 can be obtained against each single one of these queries. Okay, so resulting in a total number which will represent in this case the number of infractions or the number of violations that the compound makes against our rules. Now, if we look towards the bottom of the file, there are other kinds of queries which actually provide a count of the pattern that is sought. So for instance, for this query name hydroxyl count, it's looking, so again, it is a structure query because it's SLQ, and then we have our smarts pattern, which describe in which topological environment this hydroxyl group is to be found. And then here we're using the unique mapping, so it could potentially return a number higher than 1. And in this case, if it returns well, 6 or more of occurrences of the pattern in the structure, then there is a score of 1 that is obtained. If the number that is returned is, say, between 0 and 5, then the score returned would be 0. Okay, and so now we can close this and go to the software. And the way that we use these queries is similar to the way that we've used them before, in that you simply go to the data pull down and then select add compound attributes. Then you're going to be issuing a query, but now instead of bringing in this query from MedChem Designer, we're going to bring it in from a file. So to avoid any confusion, we're going to clear this and then load our query from a file. Okay, and in this case, we're going to bring it from our drug-like filters. Okay, so we're going to select this. And notice that it is loading the content of the file, the entire query in this window here, and it's also assigning the attribute name to be the name of the head query, which is, in this case, is DLF for drug-like filter score. Okay, and when you're ready to proceed, just press the OK button. And so it actually is a multi-threaded process, which is really quick because we just went through all of these fairly elaborate queries and applied that to our 10,000 structures. So it went pretty quick. And now it generated 2 columns, a column which is called DLF underscore score, and that is the total number of, well, that's the total score. So the number of times that the patterns were matched for each particular compound. Okay, so in our case, that's how many sort of violations or hits against that compound there were. And then there is a DLF score code, which indicates the nature of the violation against the rule. So we have a little bit more of an explicit description of what triggered that DLF score. Okay. And if we want to have access to these compounds, we can follow a similar process to what we've done earlier. First thing is we may want to know what's the range. So in this case, the compounds are doing really well, and probably similar rules were applied in the elaboration of this collection. But we only have 2 compounds with a DLF score of 2, then we have some with 1, and for the most part, it is 0. So it's really only 3 bins that we have. So we know we have 3 bins, 0, 1, and 2, and this is our DLF score. And so we have, again, the majority of our compounds are in bin 0. There are some in bin 1, and if we want to see them, we would just click on that bin and see that there are 193 compounds, again, out of 10,000 that meet these criteria. Okay, and then we can just go through these compounds one by one. Notice that the compound attributes are conveniently provided for us here, and again, it indicates the reason why there was a particular score attributed to this compound. So in this particular case, we have a terminal alkene that is in the compound. So, and we can just go through them through them. In this case, it's 5-membered ring counts, etc. And these rules are customizable. I mean, some people have different preferences from others, and it's also very much the case that different therapeutic classes also can have different rules, and some of them extend significantly beyond the sort of standard rule of 5. So again, this is just a really convenient way to look for these patterns within compounds. And you could follow the same process to create, for example, your own Payne's filters. So this is so-called frequent hitter compounds, known as pan-assay, interference compounds, which are promiscuous compounds that tend to hit very often in HTS screens. And there's been multiple papers that have described the kind of features that these compounds have, and you could use this similar sort of rules to define the kind of criteria that would correspond to these compounds, so you could potentially eliminate them from a screening collection. So what I'd like to show you now is how you can customize these rules, because so far we've used this file which had a set of pre-established rules, but it's really important to understand how you can edit these files and make up your own. So we're going to look at a fairly simple file, fairly simple generic file, and I've called it actually generic underscore ATT for attribute. And we can likewise open this file with Notepad, and I've defined it very generically. And for example, what we might want to do is use this as a template to define a query for a Michael acceptor. So let's first of all save it. So we're going to do save as and define it as Michael acceptor. So we're going to save it as a Michael acceptor query, Michael A for acceptor. We're going to call it that. And we're just going to save it. Now the query name, well, very simply stated, we're going to call it Michael A for Michael acceptor. Okay. Now we need to define this query. Okay, what the query syntax is going to look like. Okay, so the range that is allowed for the output is optional. If we leave that empty, it will just return the number of mappings, the number of times that the particular feature that we're looking for is found in each one of the compounds. Okay, and then we need to define the mode of mapping, whether it is unique, full, or single. We're potentially looking for more than one occurrence, so single wouldn't work, but in this case, we'd be looking for unique mappings of the compound against the query. Okay, and again, this may return more than one. Okay, so and now we need to define our smarts expression. So how does a Michael acceptor look like in the smarts language? So if you don't speak smarts fluently, there's a very easy process that you can go through to generate a smarts expression for the structure that you're looking for. And so if we want to define a Michael acceptor, then we can simply just draw it in MedChem Designer. So we can simply draw this as an alpha, beta, unsaturated system like this. put our carbonyl here, and we're done. Okay. And really, in order to obtain the smart string, it's very simple. Just select the structure. You can just lasso it or just hit Control A, and then go to Edit, Copy As, Smarts. Okay. And then go back to your Notepad window and just say Control V, and that will paste the smarts expression into the query, and just say save. And now this query is basically ready for use, so we can close it, and if we wish to use it in a search, we can simply go follow the same process we've done before. Add a compound attribute, query. We're going to clear the previous query we had. We're going to load our new query file, and in this case it's on Michael acceptor.at_at.cqf. Again, I put _at for attribute, and open it, and it's named it, so this will be the name of the ensuing column. Okay, and just say OK, and it will perform this search in a similar way that it's performed the previous searches, and we can look very easily how many Michael acceptors we might have in these collections, and there's not too many, and they actually probably don't even look like true Michael acceptors, but that is something that we could further refine in our smarts definition. So again, if we want to know how many is in each class, we can just similarly select our Michael acceptor column. Again, we have 3 bins, 0, 1, and 2, so we're going to leave that the way it is, and we have our 3 bins, and we can again potentially very simply go through. Sometimes if the number of compounds is really low, it can be difficult to select the corresponding histogram. I was able to do it here. Otherwise, you can just select the compound and hit that arrow to scale up the selected set. But here I was able to pretty easily select that that 3rd bin, and then we can go through these compounds, and we end up having 10 compounds that at least triggered our Michael acceptor rule, and we pretty clearly easily see the alpha beta unsaturated substructures that were called. So that's pretty much all I had planned to cover. I hope this was useful, and I wish you a great rest of the day. All right, bye now.